currents. Strangely enough, are not conserved. So when you perform a chiral transformation on, say, a quark field, you find out even if m quark is 0, so there is a symmetry, it's broken by quantum mechanical higher order loop effects, amazingly enough. And this is one of the most fundamental aspects of field theory and particle physics. It sort of plays an incredibly important role in many different branches. And we said it's, and quarks have QCD, and this is the thing I concentrated on. And I ask you to take my word for that. Then I said there were a number of statements. Then the second statement, I can write it here, is that I can actually write this as a conserved current, as a derivative of a current. Sorry.
Saying that it's quantum effect comes from a loop diagram? Or?
Actually, you can see it at one loop, and then you prove that it's true to all orders. The result I'm saying is true to all orders in perturbation theory. This is a remarkable result which is proven in path integral.
This truncated result is the first leading order into the coupling. There is like a...
No, this is a general result. This is actually true. This is a beautiful thing. This is true to all orders. It's not truncated.
Okay.
It's amazing. This among non-trivial thing to show here that it's the fact that one loop result actually is true. It was derived first at one loop. And the loop would be, the diagram would look like this if you wish. Think of here as a current. This would be a quark propagating. And here you would have a gamma mu, gamma phi current vertex. And then you would have two gluons here. And you will compute something not so different from, say, Higgs decay, stuff like that. It's not that different, okay? There are subtleties and it takes time to compute it, therefore it's not something we can do easily. You compute the derivative would be Q mu times the gamma mu dependent triangular diagram. This is how we would do it in perturbation theory at one loop. Of course, it will have no guarantee then that this is true to all orders, okay? But still, it will be useful to do that. I mean, anyone who is interested, you can try to do that. We can talk about it if you have some little time. Now, of course, you are doing your thesis. The Q, of course, is here is they will have different momenta P1 and P2. So this thing which has derivative enters because the momenta was entered. At the end, remember when you do the Higgs decay, you get a gauge invariant result just because it has to be gauge invariant. Unless you make a mistake, it's going to be gauge invariant. So I could write this as a total divergence, which we normally ignore. It's a surface there. And we even wrote what K mu is. K mu had a piece which was epsilon, anyway it looks like epsilon mu alpha beta. Then the first piece is G A alpha beta A nu A. Right, I have indices. Maybe it's better this way. And then there is a piece which has actually G over 3, and it has epsilon A B C, A alpha A beta B, A gamma C. So remember the argument we said. This cannot, so then that means, well, first let's see what it means. Okay, let's keep it here. The second important statement, let me write it here, is that then it means that the change of action is given by alpha d mu j mu phi integral, right, as you should. This is how you derive the conservation laws when the action is invariant. We have now the opposite situation in which actually, because of the non-invariant, non-conservation of current, the action cannot be invariant. Otherwise, when we call the symmetry, we say action is invariant. That's what we mean by symmetry. Then we get conservation of current. Here we have a situation we can compute the conservation of the current, therefore we know whether the action is invariant. So this is equal to alpha ds mu k mu. Properly normalized, right? There is and you and I are usually tempted to say that the surface terms do not contribute, and actually we are often right when we say that, because we ask our fields to go to infinity in order to have finite energy, finite action configurations. Perfectly true, but this piece, however, is dangerous, and in principle, who was asking yesterday, could I write it? I think maybe more elegantly, okay? This piece, for example, you can show, after all, you and I like to work with AA, which is, no, A mu, which is A mu A TA. Elegant way of writing, you're supposed to carry the generators together, because so you don't have to every time write the indices, right? We define a matrix, a joint matrix, right? That's how we actually worked a lot. And it's not hard to see, well, then this becomes, in other words, K mu will be proportional to epsilon mu alpha beta trace by the way, in general, this is F. I should have written, you agree, if I speak of SUN, and SU3 is what it is. Okay, what you can ask yourself, presumably that's what you wanted, shouldn't this be related to trace TA, TB, TC? There is no gamma, there is mu. This thing, you and I should show it's proportional to FABC. If you show that, then you can work with these directly. Now, how would you show this? Notice this is multiplied by epsilon mu alpha beta, so there is an anti-symmetry. You could write this as a half. You would write this as a half trace TA, TB, TC plus TB, this plus TB, TA, TC, and then I could call this B, A alpha B, A beta A mu C. Notice that if I put a half here, this is equal to this. This is a dummy index. But then I use the fact that because of the anti-symmetry in alpha and beta, I'll get actually a minus sign. You show then that this is 1/2 trace TA dB. Show this please times A alpha A beta B, A mu C. You go back using the anti-symmetry property. This will give you an extra minus sign. This you know is FABC, FABD, and then this would be IFABD PD. So there is a factor of Y somewhere, okay, when the dust settles. You're following this? And remember that then you use the fact that trace TCPD is 1/2 delta CD. The normalization of SUN generators is always with a half because of SU2 being embedded in SUN. In other words, this thing will give us a factor of 4, I believe.
Similar term was the one that that broke the symmetry in the first problem of the final lesson, right? When we used the...
I don't remember the final.
Yeah, well, there was a term, a similar term.
No, I don't remember which problem. What I want to remind me.
The one with the one with the symmetry breaking of the joint of the.
Oh yeah, there was a cubic term of the adjoint. There was some.
Disappeared.
Well, you could right. So I think you get a factor of 4. I think that trace of A mu, these are now matrices, A alpha. And there is important epsilon mu nu alpha beta. It's probably equal to epsilon mu nu alpha beta. There must be a factor of 4, probably 4i. I think I have an I, right, from here. There's got to be. I think. 4i epsilon ABC. So our term something like this. 4 because there is a half here and there is a half here, I believe. You can check it. So we could be fancy, and it's good to be fancy. You will see why. Okay, I'll comment briefly to sort of. Now I introduced the subject yesterday. Now I want to sort of digest it, help you digest it.
Maybe the first one is without parentheses, ABC, because it's.
It'd be much better without the indices that have nothing to do with anything. These are matrices, they don't have indices. Thank you. I mean, it's here, right? This is this, right? Trace A alpha, A beta. A nu is then equal to this, and so on, so on. So we could relate that. So in other words, sorry?
It's an FABC in the general.
F. See, I am always thinking of SU2. I can't help it. What we do actually, we isolate an SU2 subgroup of SU3, and you put there this so-called instant solution. So let me comment on that in a second. You can always embed SU2 in SU3 and look at the SU2 subgroup. An SU2 subgroup of SU3 is an SU3 matrix. In other words, an SU3 matrix is this. You agree? Let me come to that. So in other words, this integral, in other words, G mu nu, or GG tilde, let's call it, is integral ds mu of k mu is epsilon mu nu alpha beta. Let's write proportionality. Yeah, epsilon mu nu alpha beta ds mu, and then trace A alpha beta A nu. Something like this, right? This will contribute. The first piece will not contribute because this goes to 0 infinity. The thing that will contribute here, of course, is a pure gauge. When it's not a pure gauge, it should vanish at infinity, okay? Because we want finite energy contribution. But a pure gauge can be anything because G vanishes. So a pure gauge is 0. Apparently. So this is one of those things like a Aharonov-Bohm effect and so on, when the pure gauge can matter.
Is that for 1 over 4? Or?
Sorry? Is this 1 over 4 or 4? It's probably 1 over 4, I guess you're right. Yeah. Maybe better like this. Thank you, good. If you want to be careful, I just want the proportionality here. I'm thinking, I don't know how on we'll go on. If you go on, maybe actually tomorrow I do it. We discuss it. I just want to outline it for you. And then I said U alpha, no, A alpha, this matrix, will be proportional to U, remember, D alpha U dagger. This was a pure gauge, normalized. There was some normalization. So we have Professor Olak here, who actually checked today. I was busy preparing the lecture, but he checked something, okay? This, if you want to do it, if you want to really get ahead of me, or you can postpone it, there is a book of Palashpal. Remember the books I suggested? I gave you pesky notes. And I suggested various books. One was by Palashpal, which is very, very, very pedagogical. Sometimes a bit studentish. It's not as deep, maybe, as would be Coleman or Peskin. They can be extremely useful because everything is kind of computed. And what he computes, so this is coming back to Mehmet's question yesterday. I now have a pure gauge. Again, I'm looking at the proportionality only. There was I over G or something, okay, please. And then you say this may vanish. Of course, if I take U equal 1, a trivial pure gauge, A0, that will vanish. But now I have to give you examples in which, for example, U is not trivial. So look at this U. I'll erase it. So U is T plus Ix times sigma, or R times sigma in this notation, T squared plus R squared. Take this U as an example, okay? Remember what I told you, with U I can map, I can take the boundary condition for T and R very large. If you do this actually in the Euclidean space, I can tell you why. This is SU2 transformation. In other words, sorry, the SU3 rotation would be this. You agree that this is an SU3 rotation? You just have to check that U dagger is 1.
The U is 3 by 3 matrix.
It's, yeah, this is the 2 times 2 piece. This is 1 then, sorry, it's not a matrix. This is Hermitian. And what we have to do, and it's a bit lengthy calculation, okay, there is a tricky part, okay, that Charan said he checked today, and I think you had a disagreement with factor of 2 with Palash, it doesn't matter, but you get a finite results. You have to compute this properly normalized, okay, by inserting this. And you will get 1. You will get the G square over 32 pi square, G dual is equal 1. So is the claim. You had 16 pi square. Sorry, integral, I'm sorry, of course. What does it mean? How did you get this integral? Well, the integral was integral over k mu. K mu was given in terms of that, you substitute this particular u. So this is an example that you were asking yesterday. I give you an example of a well-defined SCC transformation that gives you actual non-zero. You can show that you always get an integer. Why? You follow this, right? This was straightforward up to the. Let me just emphasize here that A alpha goes to the pure gauge. At infinity. So this is the value for large values of space-time coordinates. To understand better what it means, imagine that you are in 2 dimensions and that you have a U1 transformation in which A mu, pure gauge, is U d mu, U to the -1 u dagger, whatever. U, you could write as e to the I theta, some function of theta. If you want to map, and infinity, of course, imagine that you are 2 dimensions. What would infinity be when the radius is very large? It's a large circle. So I have a infinity, which is a circle. So this would be in 2 dimensions, U1 case. And I can take a pure gauge. It's actually d mu, QD. It's just a fancy way of writing to have the same notation, okay? I did it in U1, it's not so important. So the infinity is R going to infinity, so it's a big circle when you integrate over d theta. And this U, you want to have a map from a gauge group on that circle. So in general, you have a parameter alpha for the U1, and then you say this alpha can be a function of theta, but you want it to be single valued. Okay, you want this point to be single valued. Therefore, the acceptable function, it must be periodic in theta. If I move by theta 2 pi, I want to be on the same point. So this should be an integer. This is how you get these topological integers in the mappings. This function must be n times theta. Cannot be n over 2 times theta, or some rational number 10 theta, because then you will know how to classify this point. Okay, are you on this point, and so on. What does it mean? That you are mapping a circle, you are counting how many times you are going on a circle. This is a map. If n is equal 1, you go around the circle 1. This corresponds here. To write this for general n is a bit messy, but you can do that. You find that the configurations, yes?
In U1, the pure gauge does not look like this, right?
Yeah, it's pure gauge. This is pure gauge. This is d mu and theta. D mu alpha, as we called it. All I'm saying that alpha should be n theta when I want u to be single valued. I want to be have a well-defined wave function for a mu. U, of course, can be anything, but if this corresponds to a wave function, then alpha should be n theta as a function of theta. You want to have a map of, you are mapping the space-time boundary. This goes under the beautiful subject of topological defects, a wonderful subject that has to do with domain walls, strings, and monopoles that you get in field theory when you can map boundaries in your space-time or space to the gauge group configurations. Here is an example. I have a U1 gauge configuration that gives me a map of a circle as a boundary infinity into the gauge group. I go around this large circle once. I may go in the gauge group once, twice, thrice. Okay, it has to be well defined. You can map circle to a circle. You can map sphere to a sphere. For example, if you have a sphere, then the circle itself, you could shrink on a sphere to a point, right? So you can only map circle on a circle, not circle on a sphere, and so on. So here what you do, you map, remember this is an SU2 transformation, and you map it in S3. S3 is the large sphere at infinity. But SU2 is S3. Right, when we wrote it. The representation of a sphere. What we could try to do, if you're interested to go deeper in the subject, so you will have to tell me when we meet tomorrow, okay? So today we have one lecture. You need to think about what. It won't be good if I'll take you. So let me do it 1 hour and a half. I started at 5 after or 10 after? When was it? 10 after, I think. Or 5 after. 5. 10 after. Okay, I have roughly an hour and a few minutes, okay. So I'm now summarizing and adding little pieces of yesterday, okay. We can go even deeper, but this should be just an illustration that yes, there are configurations like this one. You have to do this integral, it's a bit lengthy, but maybe fun with the help of Paul to show that you get a non-vanishing result. Okay. Remember in QED, it could have happened in QED, there was no such piece, there was this piece, and this is manifestly zero, because G is zero at infinity. Whatever configuration you would take, G will be zero at infinity, you will get zero, okay? QED had only this piece. So this is new. You can imagine the explosion of the interactions in field theory when this was realized in the 70s, just as the QCD was being emerging as a theory of strong interaction, that besides the rich homology had a rich field theory. So the bottom line was, I have to take this seriously, this piece, GG2. I can't ignore it. It's there.
The example for the new one here, we somehow assume space-time is compact also, right?
I'm looking at a two-dimensional situation when I want to have pure gauge at infinity. So I'll take in infinity to be a large circle. That's reasonable.
So in the theta direction,
Right.
For that surface, we map from the circle in U1 to the space-time circle.
This will become dx mu a mu. It would actually become dx mu, d mu, and theta, which is 2 pi n. You would emerge an integer. This would be the flux you would recognize in 2 dimensions. Well, 2 dimensions, I could be interesting maybe to go in 2 dimensions. Coleman does it, it's kind of interesting. Okay, in 2 dimensions there is something called Schwinger model which you study. 2 dimensions are very interesting. There is no magnetic field. In 2 dimensions, F mu nu is epsilon mu nu F. There is only electric field. So the analogy of F squared in 2 dimensions is epsilon mu nu. This is an invariant. Integral over this will give you integral over this. If you keep asking me, I was hoping you won't, but you are. Okay, no, I'm glad you do, I'm sorry. I just wanted to sort of be hand-waving that in 2 dimensions you could visualize how this n appears. If I give you some pure gauge, which is single-valued function of a gauge field. Whatever even without being so fancy, I said yesterday, well, in general, why should this be zero, right? No, people then sat down and provided examples, but It would be a miracle this is 0 for all configurations. They had no reason to manage. You see, we are talking about pure quantum effects. There is something miraculous happening. We are aware of what is happening at infinity. This is interesting. This physics. You see, theta is not an ordinary parameter. There is something special about theta. It's actually, we say in QCD that there are different possible vacua characterized by this integer. Why do we call them vacua? Because these are pure gauge configurations. And they can actually be characterized by an integer, depending how you are doing this strange infinity mapping.
I think I've seen the answer somewhere else, but again, I want to ask this. Since we have a gauge independency, can't I choose a proper gauge to get rid of this number n? Because I can still more apply more transformations. So
No, you can't.
I can connect to the identity. I could.
No, you can't, because this integral is an invariant. The thing that I computed is an invariant. This is invariant under gauge transformation. This was purely invariant. We just computed GG dual. If I get n, it's n. You're not going to find gauge if it's n is 0, because this is invariant. It does not depend on the gauge. This is a gauge invariant quantity. The fields are gauge covariant, and this is gauge invariant. This is the beauty of the
To
thing.
change the winding number, you would have to make a singular term.
Right. Something like that you could happen precisely, but we didn't want to have a singular configuration. We wanted this well-defined group. And this map really, you know, when you think about that, if I go about the circle twice, you cannot undo that when I'm binding myself twice. Okay, it's a topologically different situation from the one when you're going once. It's sort of like using scissors, right? Singular, okay? In topology, you're not allowed to use scissors. That's why in topology, potato is equivalent to a football. There's no difference between a terribly squashed potato and a football. So we said yesterday, because of this, we can keep this. That I will now take seriously this interaction, and I will keep in mind that this is a very strange parameter, okay, somehow. It has to do with the structure of this vacua, okay. But it's there, which I call GG dual. In other words, when I write QCD Lagrangian, we said yesterday, okay, remember we said there will be extra piece that I have to take account. Then I said, when you perform a chiral transformation, it was written there, you agree with me that theta goes into theta plus alpha. By definition, what I wrote here. The change of action is precisely alpha times the derivative. Okay? If I perform a chiral transformation, theta goes into theta plus alpha. Why? Once again, because delta S is alpha d mu j mu phi. But that's alpha GG dual. So I'm simply changing this coefficient. Okay, there is something interesting. You see already that this coupling is very unusual. For example, if a quark is massless, let's imagine just one quark. This is actually a transformation I'm allowed to take. Nothing else will change. Everything else is invariant except for the anomaly. Okay? No other piece in the Lagrangian knows that I perform this phase. Kinetic energy, covariant kinetic energy. Therefore, in this case, alpha is arbitrary. And therefore, theta is 0. I can always choose alpha to be minus theta. It's very similar to what I told you. If you have massless quarks, there is no mixing. You may think that there is mixing, but I can rotate it away. Or better, whatever you compute, you will always see that it vanishes, okay? You may not be easy to see that, but yes.
What happens to theta bar?
Oh, not yet theta bar. This is first statement. Let's erase this so that it's not confusing us. Now comes theta bar. Quarks have masses. In general, actually there is no massless quark. This is what experts will tell you. When they study the properties of quarks, they will argue there are no massless quarks. But anyway, in general, MQ, remember what I said yesterday, is UL daggers. I spent a lot of time and so did Alexei, emphasizing the importance of this mixing angle. So when I do this chiral transformation, this is just the U1 oral phase, you agree that alpha is argument determinant UL dagger UR. I want to isolate this U1 piece which has the anomaly. I should have stressed. U1 chiral transformation has anomaly, and only U1 chiral transformation has an anomaly. I could make you, what we could do tomorrow, for example, would be very useful. You can ask me, well, what about gauge? You should have asked me, if there are these anomalies in the standard model, all the gauge transformations are chiral. The left-handed SU, the SU2 is left-handed. So you can ask me, isn't there going to be anomaly? I argued when I taught you that the only way to prove renormalizability is to have this current conservation. This is why I wanted gauge symmetries. I wanted to imitate QED. So you can ask me, well, you can tell me if there is an anomaly, the standard model cannot work. True. There is a miracle in the standard model. Really, an extraordinary miracle. That anomalies exist and they cancel between quarks and leptons in a mind-boggling manner. We could check that if you're interested. Without knowing what the anomaly is, I'm sorry, because I've just asked you. Once you accept that there is an anomaly, you and I can go and check whether they cancel. At the moment, you agree with me that alpha is this. I'm performing a chiral transformation. When I do this, in general, there will be an overall phase. And that's argument determinant n. This is now finally summary of the introduction of yesterday, which means that theta changed when I diagonalize my quarks. If I start with pure QCD and electroweak theory with an arbitrary quark mass matrix, then I perform a chiral transformation, and I need to perform it to rotate the quark masses into the diagonal form. I will get the theta shifts by theta plus alpha. This is what I say here. Anytime I perform a chiral transformation, theta changes. When quarks are massless, that's a symmetry and theta disappears. When they are not massless, I get this. And then I conclude this is the physical parameter. Better to write it not like alpha, to be clear. Argument, determinant, and quark. This was the crux of the yesterday's lecture. Yes?
And one of them is massless, the bar is also zero, right?
Yeah, of course. Determinant will be zero, so the argument of the determinant will be zero.
And for transforming the quarks,
It's enough that one quark is massless and theta disappears.
and the angle in the transformation for quarks is alpha or alpha over 2?
Is alpha or alpha over 2? I don't know. I don't care. No, I mean, I do care.
UL, angle UR give us the alpha as an argument, right?
When UL is what? Equal to UR? No.
No, like in any case, this product, this matrix has the argument alpha after the transform.
You mean the way I wrote it here, is this alpha or 2 alpha? Good question. Help me. I think it's alpha, but I'm not sure. I mean, this transformation tells you that, remember there is always also this. This is a symmetry, and QED is okay. I don't have to worry about anomalies. There are no anomalies. So really, when I talk about it's always that piece which is not vector-like. So all the current transformations are invariant. They can look like this. QL goes into e to the I alpha QL. QR goes into QR. QL goes into QL. QR goes into e to the minus I alpha QR. This is the same transformation. Or QL goes e to the minus I alpha over 2 QL. QR goes into e to the I alpha over 2 QR, or maybe minus, plus the way I define it. All of they are equivalent because the difference is a vector-like transformation, okay? And all of these give me alpha. I think the way I wrote it, this is precisely alpha. I think. If it was 2 alpha, who cares? I don't know. You see my problem. I don't know what argument determinant is. And I have no way of knowing. In the standard model, this is an arbitrary quantity, and some people, I remember they said, why should this number be small? So some people said, well, I could even call this a problem. Why is this number that should be of order 1? Why is it small? But that's sort of, Eddington went crazy, spent all his life trying to compute why is alpha of QED 1 over 137 and not 1. And you can ask him, why is electron mass 5 orders of magnitude smaller than W? No, why am I taller than Nicolas? I don't want to answer that. Okay? Dangerous question, do you agree? So that by itself I don't know what to say when you tell me. So I said yesterday, however, we can define the problem that everybody agrees on. The problem is called, remember, if you have some physical parameter, how should we call it, not to call it theta? P, parameter P. P is P3 plus P loops. I can always separate it, right? If I can compute P loops, and it's not a question we were just discussing in the car, Sharon and I, if I can compute P loops somehow, and if I can show that P loops is much better than P experimental, then we call this a problem. And we call it the problem of naturalness and or fine-tuning. It says, if this is true, then this also must be much bigger than experimental. And you have to cancel these two. This is called a problem of fine-tuning or naturalness. This is not natural, people say. We say then, this has become accepted, then this parameter then is unnaturally small. And that doesn't depend how big it is. It's not because theta is 10 to the minus 10 or 10 to the minus 5 or 10 to the minus 2. Whenever you have, you can have even that with a parameter of order 1 over 100. If the loop was much bigger than the... Now in many situations, loop is proportional to the 3-level situation, then you don't have to worry. But maybe you want to, okay, I have time. Maybe you can slow me here. Maybe we can still try to recapture some of these technical things. Oh, this was very important. How do I know what theta is? Okay, the Mehmet was not happy with that. I said, if I compute the electric dipole moment of neutron without knowing how to compute the electric dipole moment of neutron, I would say it is theta bar over lambda QCD. That's the only scale. And since in the limit of quark mass, this goes to 0, I would just estimate like that. And then Mehmet asked me, but there are no quarks when you compute electric dipole moment of neutron. Right? When we have very low energy, this is low energies, this is this amazing thing of strong coupling. When I'm at high energies, and strong interactions are actually not strong, we can speak of quarks and gluons and so on. When we lower the energy below GeV, the language should change. There are no quarks anymore. It's amazing how dynamics, it's not just the capacity to compute. You even don't know a priori what the theory will be. Like when we get close to a Planck, we don't know what in the world this will look like. In QCD we know because that's how we started, you know, we went from there. We knew it. We were in the strong and then we went to weak, okay? With gravity we'll have to do the opposite. All I meant to say is not that I'm computing this, I'm saying this is just a dimensional argument. This has to be addressed. There are no quarks, just like K long, K short, okay? I want to invite you. This is not so stupid, even if it's a language bad. And remember, look how I'm saying, you know, I'm not working with quarks. I'm just saying something incredible happens here, which is QCD dynamics, something that saturates this theta bar through this GG condensate, you know, something happens there, some kind of blue ball, whatever. And so I get the result. What else should it be? I said, dimensionally, that's the only scale. And only I wanted to add that. Anyway, it turned out to be good. This is about 10 to the minus 16 theta bar centimeters. When I put in centimeters, that should be less than 10 to the minus 26 centimeters. Therefore, theta bar is less than 10 to the minus 10. So now the question is, it's not the smallness of the parameter that should vary, because we have to compare it with something else when we say that something is small. So people used to say the following: this is very small compared to the CP violation parameter of the standard model. And that was naive, because the standard model CP violation goes through another scale which is much bigger, and so on. Be careful, I said yesterday, when you make such statement. And I'll summarize it now for you.
By the way, we can every time choose our determinant m to be equal to 0 and with theta s theta bar, right?
This is sort of the, you can do that, and then you will run into this question that may become a problem. You chose it to be 0. You proclaim it. You said, look, it's not measured anywhere. I don't know what it means when you say that we can choose. What do you mean by that, by the way? I often ask myself, I have written papers when I say that I choose something. What does that mean? You're telling nature how to behave. Remember, you're playing God at that moment. Why the hell would you say that? To whom you are saying that? To Talal, to your peers, to me? A smart person says, I don't know what it is, let me look and wait. But it's useful to do it still, to say, if I set it equal to 0, will it stay 0? Why are you asking that? Because this number is very small. This is 0 for practical purposes, okay? That's much smaller than any dimensionless number in the standard model, except for, I can form some very dimensionless number and try to understand it. For example, the ratio of mu on lifetime. You know, when people tell you that some numbers are small, tell them to tell you in which sense, always. Look at this number. Lifetime of a muon divided by lifetime of the proton. This is much smaller number. How small it is? 10 to the minus 6 seconds, and this is 10 to the 41 seconds smaller. This is less than 10 to the minus 47. So I say theta bar is very big compared to this number, okay? It doesn't matter here, but You could tell me, why don't you warn in the standard model that proton lifetime is so big? We could spend, we can go crazy trying to think in the standard model. And we have no answer. Fortunately, the standard model doesn't predict proton to decay, so we say, okay, but if I take it seriously, here you say, however, remember what I said, the proponent of the problem language says, there is CP violation in the standard model. And it's much bigger than 10 to the minus 10, so I expect this to be large, she says. Okay, then you do the following, what you just said. You say, okay, I will take argument determinant MQ equal to 0, and see how stable it is. Now I have to compute the loop. Who remembers what we said yesterday? It started like this. M is M0 plus a loop correction. Now argument determinant M is e to the trace logarithm n. And this is e to the trace logarithm m0 plus epsilon. Approximate. I'm doing now perturbation theory. I'm saying that m0 is corrected. The elements of this is much less than 1. I don't know how to call it. The relative I'm saying correction is, it will be justified, you will see, in calculating this. Now, you said, let's take this to be real. So the argument determinant n is imaginary trace epsilon. Okay, this is the first thing that Ellis and Gaillard said. It's hard paper to read, but when you manage to do this beautifully, brilliantly. Actually, I may be one of the few people that have read a paper by John Ellis. John Ellis, I think, has 750 papers and so on, and nobody reads his John Ellis papers because they are not papers, they are conversations. He wrote some beautiful papers, this one in particular, it's really mind-boggling. It's interesting that people that invite him everywhere, I find out, never read his papers. So, okay, you agree with this. Now I want to see, so I should call this loop, you agree? I'm now checking this reasoning. If my parameter loop level is large, then you and I will decide whether there is a problem.
So they calculated the loop corrections to the mass matrix and wrote them as proportional to the original mass.
Well, yes. Why does it go? Okay, good. Charan question is good. You see, why does it go like this? Because let me remind you, they are looking at I should be a little clear here. I'm cheating a little bit, okay? And he caught me. When I compute the correction to quark mass matrices, there are all kinds of contributions. I'm interested in one that can be complex. Remember what I said, I will work with physical quarks whose masses are real and positive. For sure real. Okay. Therefore, I'm now interested whether I can generate a phase at some loop level. That can only go through W. You agree? The only source of complexity is VCKM. Everything else is real in the standard model. Gauge coupling has to be real, the Higgs coupling is real, Z coupling, photon coupling, whatever we do, everything is real except for V. Okay, this is the subtlety here. Therefore, the loops go like this. A quark enters, for example, an F quark UL. There is a W that I have to exchange because I'd like to generate somewhere something complex. When I do that, the left-handed quark will remain left-handed. So the chiral shift, the mass is external. You see, this proportionality turns out to be true because this will always be on the outside. There is no way you can manage to have a single change of chirality here. If you enter left-handed, you have to come out left-handed. Okay, this is very important. Here, mind-boggling thing can happen. I have complicated propagators that may make, that I may have mass insertions, but if I have one mass insertion, I must have two. For example, because this is W, UL becomes DL. DL can become DR, but it must come back to be DL. So the actual current change is outside. In this calculation is correct if I concentrate on the complex contribution to the original mass matrix, which, by the way, is this mass matrix in this basis is real. There was, in the process, of course, there was this argument determinant MQ, which I don't know what it is, and we took it to be 0. But now we are working with real physical quarks whose masses are positive numbers. So we needed to compute, this is what they do, and this is the part which is hard to read. And you shouldn't blame that you have to read. When you write original papers, it's hard to read clear original papers unless you're called Weinberg. Okay, basically nobody manages it. Because usually we're confused. When I look at that paper, I think they may have been confused, I'm not sure. But the message was clear. So, we said this trace of epsilon, I had to isolate what is the minimal structure, how many W's I have to propagate. Remember the reasoning. I will have a trace. I start somewhere here, and remember I could have loops here. I have all kinds of loops everywhere. I start with V. Let's call this V. If not, maybe it's V dagger. Doesn't matter. Then there is a mass insertion of some species I call down, and it has to be even power. I'm going through, let me write that. Let me draw that. For example, this one. V, then maybe some mass insertions, then V dagger, V dagger. How do I know it's V dagger? Look, this was a up quark. So it's V to become a down quark, so this is a down quark, then of course they are V dagger. No, that's right here. Trace epsilon is trace V M down to 2I, V dagger M up to 2J, it must be even. Again V M down to 2K, V dagger M up to 2L, and so on and so forth.
Mass insertions are numbers or matrices? All U type?
They are diagonal matrices, of course. This is a matrix, this is also a diagonal matrix. Remember I said yesterday, cut it off here. You ask yourself, this is how they did it at the end. Then you think later.
When you say mass insertion, you use massless propagators for the clock?
Afterwards you can use a massless propagator if you wish. You see, every time there is a mass insertion,
We are treating the mass as an interaction.
as an interaction, as a perturbation. Why am I doing that? Notice, because why am I doing that? Okay, Charan was not here yesterday. If I don't put a mass insertion, I immediately get rid of the complexity. I get VV dagger. So they said we are forced to do it. Every time they do it, of course, the integral is becoming better and better behaved. They become more and more Feynman because now I have 1 over p squared every time and so on. Okay. But the point is here. I need to start putting this. I said yesterday, the first attempt you and I tried to do was to cut it off here. It didn't work. This was real. It was trivial to show that this is real, just by using the cyclic property of the trace. This one we studied. We stop here to try our luck.
No, it's real. If you put the line just to the right of the V dagger.
I put here. If you put right of the V dagger, that's even more real. That's terribly real.
Why is that real?
This here.
Yeah.
Okay, let's check it again. I use the following fact: the trace of x dagger any matrix is trace of x star. Correct? Now I'm computing imaginary trace x, which is trace x minus trace x star, which is trace x minus trace x dagger. Sorry. Correct? So let's compute it. Let's take x to be this, what Sharon is asking. So what would be x dagger? So I won't write x. What is x dagger? Help me. So trace x is trace x, which is there, minus trace. So dagger, first mu, I'll be pedagogical, mu to j, v, md to I, v dagger. Correct? This is trace x. I will move now this here. Let me use the privilege of the blackboard. Cyclic property. Notice that it's the same matrix as before. There is an incredible thing, you know, they asked yesterday, we didn't push it enough probably. There is a strange miracle in the standard model, the way it works. There is something crazy in this conspiracy. Now you do the same thing here. So take x to be this. By playing in the same manner, we found yesterday that if E is equal to J, remember we got trace x equal trace x dagger immediately. But just using the cyclic property. Okay, you will see that in a second, even faster. Of course, if that means also if K is L, there is a complete symmetry between up and down. Every time you have an up quark, you have a down quark, up quark, and so on. Okay, and you in the end look at both up and down quark matrices. They both contribute. So we found out yesterday I will say something new today, but very little, on purpose. Good. Because you would have been lost if I had started reading new material. We found out yesterday, imagine now I can estimate the argument, determinant, and radiative, or loop. It's this imaginary trace epsilon. That is surely less than equal, because you and I are not doing the calculation. In order to get 4 V's, I need at least 2 loops. At one loop I get 2 V's. Maybe I need more, but I need it because of mass insertion. I need at least 2 loops. You agree? When I have one loop, I get V and V dagger in order to have 4 V V dagger combinations, I need at least 2 loops, as I draw it. So this is less than equal to alpha over 4 pi squared. Then I have n down quark. I want to get as large a result as possible. I want to see how bad the situation is. So I take I equal 1, j equal 2, because j must be, not j, k. If I is equal to k, I'm sorry, you compare down with down. And if j is equal to l. So I take I equal 1, j equal 2. That means I have n down squared and n down to the 4th power. I'll take the heaviest possible quark. It's unlikely that I will have, because of V, bottom quark. But maybe, I just want to estimate the largest possible contribution. I'm being extremely cavalier. So I'm saying I will get NB over NW. I didn't write the normalization, but of course the only scale is the weak interaction scale to the 6th power. Okay, I want to do this slowly. I want Sharon to... It's impossible that way. I even know if one of the quark is massless that I'll get a 0 result. I won't just get large, but that's I'm sure. But anyway, since I'm not computing, I will just to see how large it could be.
Why don't we take the top?
Sorry?
Why don't we take the top?
I will take now top, also 6 times. Do you agree?
Down, that, up, that.
There is a complete symmetry between up and down. It's at most this, and it must be proportional to epsilon CP violation. Actually, it should probably be smaller because it should be proportional to theta 1, theta 2, theta 3. I took M top out. Now I should put what? Remember the CP phase must be proportional to 3 mixing angles. It could be worse because I'm picking up the bottom quark. Maybe I have theta 3 to 3rd power, I don't know. But this is the minimum I'm gonna get of suppressions. In this estimate, of course, I took M top to be equal to MW. I can make you happy, okay? Let me make Mehmet happy. So I took this 10 to the minus 2. This is actually even small, but then let's take 10 to the minus 2. So that's 10 to the minus 4. And B over MW is 1 over 20. But n top over NW is 2. So I'll cancel this 2, so that's 10 to the minus 6. And this is roughly 10 to the minus 5, 6. Okay, I'll take the largest possible number, 10 to the minus 5. Phase of order 1. Theta 3 is roughly 10 to the minus 3. Just to remind you, theta is 2 to the minus 1, theta e is order 1. Cabibbo angle is not that small. It's actually 1 over 5, but this is a little bit bigger than 10 to the minus 2. Roughly, let's take 10 to the minus 5. And this cannot be that big. I got 10 to the minus 15. They actually did a calculation. This is remarkable. It was corrected. They made some minor errors by Kriplovich in Russia and some other people. They actually got 10 to the minus 19. Why? Because I think they got some light quark entering here. It cannot be just M top and M bottom. Because of the mixing angles. You know, if I only took M top and M bottom, there would be no generations, there would be no mixing angles, by the way. Right? I cheated it. But I wanted you and I really see this. We don't have to rely on their calculation. I don't care if it's 10 to the minus 15 or 10 to the minus 10. It's 5 orders of magnitude smaller than the experimental bound. To lower down the experimental bound by 5 orders of magnitude will be 50 years. It's been going so slowly, okay? Even you guys have become old. But we can talk about it when it's done. Of course, you think I'm old.
You're saying it's okay for it to be small because the loop corrections are small.
It cannot be called a problem. It's still an interesting puzzle that you say, why in the world is happening? And I have I have no idea why I want it to be small. What I then said yesterday was a bit stronger. I said, not only there is no problem, you will never, well, let me come to it before I say it. Typically when people say to it, they want to understand why a number is small, then take some other model, which they will postulate some other symmetry. I'll tell you about that. In order to get it, you will have to take something else to be small without any reason of knowing why it's small. You can never do better than the standard model, because in the standard model it wants to stay small. And asking someone, why is alpha 1 over 137? Why the planets are so far from the sun that drove Kepler crazy? Why the quark masses are what they are? Why the cosmological constants is what they are, as people tell you? I think this is crazy. I wasn't always, I remember I was in my early 30s when I spent a sabbatical in Santa Barbara working with the sort of us young lions, Daniel Wheeler, Tony Z, Frank Wilczek, and we would work on explaining why quarks are light, why masses are what they are. There was Wolfenstein he looked old to me. It's terrible, because you will tell me, of course, it's wrong, but he was younger than I am now. And to me, he looked old. And he was wise. Wolfenstein was born wise. You should remember this name. He's one of the grandfathers, if not the fathers, of weak interactions. I think the last Fermi student. Wolfenstein is saying, you guys are crazy, you will waste your lives, just like Kepler wasted his life. How can you ask why numbers are what they are? That's the end of physics. Physics is related to different physical phenomena in a coherent manner, but not asking why your parameters what they are. Okay? It sort of sounded conservative. At the end, 40 years later, almost, we say the same words. So I'm now converging to that point of view, and I see that everybody that writes a paper, including myself, so let me tell you what I did about the strong CP problem. I'll talk about the axiom, which is more profound and more complicated. The reason I will do what I did is because Nicolas actually asked me, but shouldn't you look in a left-right symmetric theory? That's a natural place to look at, because there, theta becomes a meaningful parameter. Because theta is something that breaks left-right symmetry, so there you can ask the question. In the standard model, left-right symmetry is broken anyway, so you cannot ask the question, why is theta? Or why is not? So let me go to that. And that will be light and easy. I won't bug you with technical points at all. So maybe today, is it sort of slowly emerging, the picture? If it is, and if you're still interested, we'll discuss the axiom, which is not easy to. I don't know. I'll have to sort of cheat at some point. There's some non-trivial technical things that would take us a lot of time. So summarize the standard model situation, just to see if anybody can do better. In the standard model, theta bar is theta plus argument determinant m, which I separated in theta plus argument determinant m0 plus argument determinant u, and I said this is theta plus argument determinant m0. I could separate this. This is one of the very unusual situations that you can compare the loop. You can actually compute it the way that Hoff wanted you to compute, and it's not related to the tree level. I set it to 0 and I managed to get the numbers. In other words, I computed the relative number here. The loop is 10 to the minus 10. This is less than 10 to the minus 10. So once again, there can be no problem because the experimental value is much bigger than the radiative correction. Not much bigger, infinitely bigger. This is one of the most protected. It's crazy that we call this the problem. Okay, it drives me crazy because it's one of the best protected quantities in physics. The degree of protection is unnecessarily large. What is a zero, by the way? I don't know what zero means. What do you mean when you say that something is zero? What you're saying you never see it? Okay. It's not a very profound statement, zero in physics.
I mean,
Experimentalists don't know what you mean by that.
but at least theoretically, if we have a zero that equals zero, so no GG filter, is it a special point or not?
You tell me.
Experimentally,
I-
we never know.
Are you happier if I tell you that proton lives forever? You are saying it lives so long that I cannot stand that it lives so long, so it should live forever. This is exactly the same reasoning. In that limit, I have an exact barrier number symmetry. I can live on that point. I'm saying that point is not special because I can move continuously from that point. Like isospin. When I have global symmetries, I can move continuously from the point of symmetry.
For example,
Theta gave me more symmetry, which is CP violation, but there was nothing sacred about being at that point. I tell you what good physics is. Instead of worrying whether protons should live forever, if you manage to do what grand unification did, that our generation could resist work on, okay, I've been working most of my life, and Charan here started his PhD school working on that, and well, he's not very great, but he's aging just like me, doesn't show it, okay? He's still working on grand unification because grand unification tells you, instead of you constantly debating each other whether it's zero or close to zero, it actually, it's a micro fundamental theory that computes the lifetime. It computes the departure from that point. That's what good physics is. To find a mechanism to see whether you live on a zero or not. And grand unification says, no, you don't live on the infinitely long proton lifetime, but you live almost on infinitely long proton lifetime. It's about 10 to the 34 years. And we are there. Imagine a theory that makes such an amazing prediction. That's what I think is a good physics. It makes a prediction with experiment.
What if someone would come and say that maybe there is a fourth masses per generation that makes that value to be equal to zero?
That there is a mass quark?
Yes.
No, the quarks are heavy.
Yes, we know, but like, hypothetically, maybe there is a fourth generation, and I know that
If the person comes, throw them out. Yeah, you just learn another one. You say, go to take Warren's course, and you know.
If it's massless, why haven't you seen it?
You would have seen it. No, we have seen all the light particles. No, by the way, the fourth generation doesn't exist. We know that. Let me remind you. The LHC now has pushed limit. If you had a fourth generation, masses would be so large. Remember that masses, Yukawa times Webb, which is actually G over 2 mass of the fermion MW when we put the numbers, remember? No. What did I write? Yukawa is, I'm sorry. Forget. Yukawa is G over 2. I'm sorry. I can write only in one direction. Yukawa fermion is G over 2 and fermion over MW. For Yukawa top, just to remind you, is 1. They're still perturbative because we tend to be okay when Yukawa over 4 fermion, if it is less than 1 over 4 pi, when the couple, this is like alpha, we are still perturbative. Okay, this is still fairly perturbative. Now the limits on the fermion masses have gone on into hundreds of GeV. So in other words, the fourth generation has Yukawa 4 is bigger than 4 pi. It's not perturbative. Then there is no standard model. Then all the calculations that we perform in the standard model that work up to the 1 in 1,000 would be purely accidental, because now any loop with this third generation will contribute equally as any loop before. It becomes like QCD. That cannot be. You're saying, well, I don't believe you. I don't care. I don't care your ignorance. Now, how do we produce the Higgs? Do you remember? What is the main source of the production of the Higgs in the gluon fusion? Okay, it was not. It could be from other things. It turns out that there are so many gluons that this is dominant. And this gives you perfect agreement with everything we are learning. You know, Higgs is becoming a high precision theory. I wish I'll show you a picture tomorrow. I wanted to check for myself. I was giving a talk in some places on how to probe the origin of neutrino mass, so I wanted to see how good is the probe of fermion masses. So Yukawa top, Yukawa bottom, and Yukawa tau are perfect agreement with the standard model. I'll show you the diagram. In other words, top, bottom, I made this joke. You know, people make fuss, it's okay if you relax for a few minutes. People make fuss about anthropic principle. And actually Weinberg is someone who sort of revived it. You may have heard some 20 years ago or so. Maybe you remember that in movie days. He wrote this paper saying that cosmological constant has to be what it is, so that you and I can be here and talk about it. It turns out that that's in order to get the galaxy formulation and so on. Rocky Gold said once that why would you worry about the anthropic principle if you don't have a perfect English accent? Anyway, I told you this joke of what Weinberg said about the anthropic principle, right? So Martin Rees is a distinguished astronomer, Sir Martin Rees. He said he's so sure about the anthropic principle he can bet his beloved dog's life that it's true. That's nothing, says Linde. I can bet my own life that it's true. That's nothing, says Weinberg. I can bet both the dog's life of Martin Rees and Linde's life. I'm so sure that the anthropic principle is good. So obviously doesn't believe it. So, you know, people ask always why there are 3 generations. I said if I were Weinberg, I was giving a talk in Texas, where Weinberg grew. Then you have an anthropic principle. The 3rd generation must exist so that Weinberg and Glescher, the fathers of the standard model, can actually see that it works. Because the 2nd and 3rd generation is going to take a long time. But the point is now that this is really a high precision theory. And this goes for the top loop. You know, we are verifying everything here. Imagine the 4th generation. You would have T prime and V prime. And the loop adds up. Right? So that previously there was just a top. Now 1 becomes 3. There are 3 heavy fermions contributing. When you square it, you get 10 times bigger production rate for the Higgs. That's we may have some tiny error, but not a factor of 10. You understand, right? That every heavy fermion contributes equally here. Because the loop goes as 1 over the mass, but the coupling is proportional to mass. So the mass disappears. You actually check that. Or we checked that by logic, or you checked it in the final. You computed, some of you probably computed the top loop in the Higgs going into 2. Who did it, by the way? I didn't have time to look. Visharit did the job. Nobody did it.
I tried to do it, but it takes so long.
Yeah, I agree. The reason I repeated it because Visharit 2 years ago, he did it, okay? Nobody ever does it, but I'm still mind-boggled. Actually, he had a mistake, so anyway, that's something we can discuss separately. At the end, I was careless, and so was my tutor. We found the mistake, Visharit and I, and we were discussing how he did it. It's hard, I agree. But anyway, but you understand that how it goes. There is here M of the particle, heavy fermion, and then there is only heavy fermion contributes. And then you get 1 over M fermion from the loop. You will see dimensionally. So you just get 1. But 1 will become 3. This is top, A prime, B prime. And that's the amplitude that you have to square. There are 3 generations, not 4. If there are 4 generations, they're very heavy. The only quark that could be massless, and what do you mean when you tell someone that the quark massless? And by the way, you understand that you are not explaining anything. If he asks you why zeta small, you say because that quark is light. Why the hell should that quark be light? So light, in other words, 10 orders of magnitude or more, smaller mass. Now, let me finish for today why the question becomes meaningful in a left-right symmetric theory, because the idea of left-right symmetry was to explain parity violation dynamically in weak interactions. So we had SU to L plus SU to R. There is also U1. And there must be a left-right symmetry, let's call it parity. Left-right. For example, just to appreciate what happens, imagine that I now write a Yukawa interaction. How would the Yukawa interaction? I would have U bar D bar L. According to this theory, let's look at this. There is U dL, but there is also U dr. There is a Higgs doublet living connecting these two worlds. It's actually a bidoublet because left and right. Left doublet, right doublet. We call it bidoublet. And it looks like this, the coupling Yukawa, phi, UD right, plus Hermitian conjugate, U bar, D bar R, phi dagger, Yukawa dagger, UDL. These are generations, so Y is a matrix, right? Something like this would be Yukawa. Notice that by left-right symmetry, UDL goes into UDR, and phi goes into phi dagger, you agree? Which is very natural because UDL and right transform under this respective left-right symmetry groups. In order for this to be invariant, phi transforms, notice, as UL dagger, phi UR. It's a bidoublet. It's a doublet on the left and doublet on the right. It's actually a matrix. But it's okay. And so you see, phi going into phi dagger is obviously a natural transformation property because this goes. Everything is natural, except now I'm also saying that Yukawa must be equal to Yukawa dagger. So if I take the left-right symmetric theory series, I want to attribute parity violation to spontaneous symmetry breaking in nature, not as in standard model. This was the original idea, whether one likes it or not. Is a question. I should take Yukawa equal to Yukawa dagger. The question is, with what precision should I take it? Perfect precision? Should the left-right symmetry be absolute? If you and I believe that it's absolute? We can write then now we have theta bar is theta plus argument determinant M is Yukawa times phi. Correct? Phi is a general complex. See, now, of course, if phi were real, you and I would conclude that this is zero. So how we would reason, this is how Mohapatra and I reasoned in 78. We suggested this in Howard, Georgia, independently. He used the CP violation spontaneously. The idea was the theta parameter GG dual breaks parity and CP. So we said, why don't we start with a theory where P and CP are spontaneously broken? Then the thing is calculable, so we said, that means that the underlying Lagrangian P and CP are good symmetries. P or CP, well, here P, spontaneously broken. This is the idea of left-right symmetry. This is the theory that actually originally developed by they didn't take it seriously, strangely enough, Patti and Salam, as beautiful as the idea was, okay. They somehow didn't pursue it, but it was actually suggested here, in summer of 73, I think. Patti and Salam. I told you this strange thing when I encourage you to take yourself seriously sometimes. You know, you can have great physicists not do something trivial, strange. They even said that it could not be spontaneously broken. And Salam was not completely stupid. Cite Pauli. So then you say, aha, so theta should be 0. And Yukawa should be Yukawa dagger. So in other words, you see, you related the value you would claim of theta bar to the physics of left-right symmetry. The problem with that, when you say that you have this is a global symmetry, in order for me to have a dynamical theory of weak interactions, I don't need the symmetry to be exact. All that is needed, that spontaneous breaking is dominant over explicit breaking. There could be some explicit breaking, maybe from gravity coming. I don't know, ignore gravity, I don't know what gravity does. You may have heard that black holes don't like global symmetries. It's called no hair. The only thing that black hole remember is charge. You know why. Okay, let me just be brief here. This is an argument which is a bit superficial. You say black hole. The problem is with the black hole that you don't want to get too close to it. Okay, actually you could go, you and I can go very close, and for example one global symmetry is baryon number. But the trouble is if we get close we cannot send the information back. But I can measure charge here by Gauss theorem. I don't have to be close. So there is sort of a no-hair theorem. I don't think it was ever proven exactly. That the black holes have only gauge symmetries or angular momentum or whatever, but not global. So if, of course, you like this, if you like exact global symmetry, then you will say that, okay, Goran tells us what is going on. Theta is 0. Argument determinant of Yukawa is 0. Everything is in this vacuum expectation value. We are making a prediction. The theta bar is the, how will you say, imaginary of phi. You agree? This is what is inducing the imaginary value of the phase. And that has a physical implication. Unlike the standard model, when you say that this phase is 0, you're making some statements. You can go on and compute some properties in the... All I want to say here, that this being 0 or 10 to the minus 10 is equally good for left-right symmetry. Nothing that I tell you about the predictions for WR physics and so on will change if left-right symmetry was weakly broken. So this is an example of what I don't like. It was interesting. I spent a week fighting with Gia Dwali, who spent his life like me on this. And I was criticizing the axion. He managed to convince me about the axion. Now he called me, he says he likes this a lot. I like it much less than I did when we suggested it, because what bugs me right, in the standard model you ask me, why is theta so small? I didn't know. Now I tell you, theta has to be really small because left-right symmetry has to be exact. So why does left-right symmetry has to be so exact, you should ask. I'm asking myself. It's the same thing, approximate baryon number is a very useful symmetry, approximate isospin. It doesn't have to be exact for us to be useful. Approximate left-right symmetry is very useful to understand the dynamics of weak interaction. You suggest the existence of WR gauge boson. I can make some predictions in the experiment. They will not change if theta was 10 to the minus 9. Nothing what I tell you about Fermion masses. Nothing what I tell you about scattering. So I would say that whoever claims that they have a solution will always do something analogous. Because 0 is not a special point. And once again, 0 is a special point in gauge series. Then it's different. You cannot break gauge symmetry explicitly. You don't know what the theory is. That's what Hoff taught you.
Well, what does this interchange symmetry between left and right, which you call parity, what does that have to do with the parity norm invariance of G dual for QCD?
That's a good question. Okay, you are saying the same thing that Via Bali was saying. He's saying Well, even if you postulate the thing that could, because this is a dynamical quantity, this would break that symmetry. You shouldn't think of this as a parameter. Notice that actually, and I think this is right, because GG dual is not an ordinary parameter. This is some strange surface term. Something crazy is happening that is contributing. It has to do with the vacuum structure of QCD. Why couldn't the vacuum structure of QCD break left symmetry?
No, but do you
I agree.
check that in your left-right model? That
I can't. No, I can't because
parity, the breaking of that thing actually feeds into that.
you see, the problem is that I don't know what I can. This is you were not there yesterday, and we were worried. If we could find a way of measuring theta separately, then this would become a physical question. Unfortunately, nobody knows how to measure the GG dual expectation value. Once this would be done, and that will be the solution to everything, that we measure this separately. Unfortunately, we are measuring this combination through electric dipole moment and similar quantities, and that's a problem. We cannot separate this from this. So these are sort of words. However, I would say logically your objection should be okay, because why should I have to impose? All I can say that the consistency of a left-right symmetric theory, I can show you it's consistent, requires that these are Hermitian. This is very small. When I say zero, I mean very small. And that is consistent. I can show you then that it's not renormalized. And it is given by the vacuum expectation value of this field. It's not renormalized. Okay, there was a paper actually on this, following our idea recently. My younger collaborators, Nemevshek, who was actually a postdoc some years ago here, and basically actually did a good portion of PhD with me. And my they wrote a nice paper, if someone is interested, showing how this is stable. In the standard model, what keeps theta stable is a miracle. Here, what keeps it stable is a left-right symmetry. Whether I'm allowed to assume it or not, it's a separate philosophical question. However, once it's assumed to be small, the same left-right symmetry keeps it small. You know, the argument like the electron mass, we don't have to worry because there is a symmetry, chiral symmetry that protects the electron mass. That's what Hoft likes. At Hoft likes, it was interesting when I talked to Hoft last year about this. I don't know whether we understood correctly each other in what we said. It seems like he would accept this solution because if you have a symmetry in the limit, you see, in the limit of these things going to zero, I get more symmetry.
No, but even in the standard model, when you calculate the loop correction, you find they're very small, but you don't know why they're very
right. What is the protection mechanism? There is no symmetry that guarantees.
But now in this case, what was already small is being guaranteed to be